So, good morning, everybody. So, today we have quite low attendance, only 16 participants, including me. So, let's just wait. Maybe some people are not early risers. Okay, so let me turn on my camera so that you can see me. Okay, so I think today we are going to be a small class. So, I think it's good from the perspective that we will be interacting more. So I want that whatever questions you guys have, you just unmute yourself, and then it is very, very helpful for me also, so that I know that I am talking to people, because you have to imagine this in the way that this is like a virtual class, so I cannot see anyone's expression, because in a physical class, even though you are not interrupting the teacher or not asking questions, the guy or the tutor can look at the faces and guess what students are up to. But now we are like far, far away. I am in Pakistan, and you guys are in, I don't know, Germany, or I don't know what else part of the world. So it's quite challenging. So with that brief motivation, so I would just encourage you guys to please interrupt me and ask questions, raise hand in this Zoom meeting and ask questions. Okay, so yeah, that would be really helpful. So let's talk about the agenda for today. So the agenda number one is that we talk about SVM lab. So I've already uploaded the exercise sheet on Moodle, right? Because if somebody is interested, they can just download it. And then we will have break. Okay. And then after the break, we will be talking about some very important topics, because these are the topics which I think Rayan already covered earlier. Um, but I think they're worth going again and again, because anyone who has taken any course in machine learning should at least know these basics. So that would be like variance by trade-off and some related concepts, right? Okay. Yeah, so and some related concepts. So and then we will conclude this session. Okay. Yeah, that's all. So let's get started with the SVM lab, and especially I want that you guys participate or ask questions in this session, because I will also be asking you guys some question, because I think Ryan already uh, discussed some of these things, right? So I want this to be very interactive. Okay. So without further ado, let's get started with this SVM lab. Okay. Okay. Mm. So now you can see my screen, right? So we have a task for the support vector machines, and again we are dealing with this MNIST dataset. So we prepare a training matrix X train that consists of first 500 vectorized training samples of digit 1 and 2 each. Okay, and then a corresponding label vector y, and like we used previously, we have two classes, 1 and -1. So 1 would correspond to one digit and -1 would correspond to the other digit. Okay, so that's how it is going to be. So now we just I mean, we just do this. Okay, we go step by step. So we import the required libraries. Okay, numpy, the pyplot, and ImageRead. And if you remember from the last tutorial, we import this convex optimization library, right? From that, we obtain some solvers. Okay, there are also other ways to do that, but we are just using this convex optimization solver for the purpose of this tutorial. So, for example, if you are going into let's say advanced courses in machine learning, then probably you you would already be dealing with the high level frameworks like PyTorch or like TensorFlow, okay, or Keras, yeah. So they already have quite decent and quite efficient implementations integrated into their framework for the convex optimization, and also sometimes very very interesting loss functions. They're like already well integrated into that framework. But for the purpose of this course, it is like a stepping stone for you guys to enter into the machine learning area. So it is always good to know what is happening under the hood. So this is, in some sense, in a very big picture, this is what is happening under the hood in those frameworks. Okay. So yeah, and definitely, if you know what is happening under the hood, then it helps you sometimes in using the frameworks more efficiently and also devising a solution more efficiently. Okay, so yeah, so we have 500 training sample, right, for D1, D2, blah, blah. I hope you guys are already familiar with this MNIST dataset because we have used it for quite 2 or 3 labs at least. So I'm not going to go into detail. So we just load this into this X train and we simply load this Y train, right? These are the images and these are the trending labels. Okay, then we said that consider the question 8.3 in the lecture 8.30 in the lecture notes and implement a function solve dual SVM that return the solution lambda star of the dual SVM problems by means of this convex optimization library. Okay, so this is the 8:30 equation in the lecture notes. So probably some of it has not been covered in the lecture. What are we going to discuss today? But yeah, I think if you guys can just correct me, have we already discussed the dual SVM problem in the lecture notes? Because I was not there in the last lecture.
No, I think we haven't. We stopped at the KKT conditions.
Okay. So yeah, so for that reason, I would just say that we will cover in the next lecture, hopefully, because there was a bit lag in the lecture because of one missing lecture, right? So yeah, so we have to cover this today, and there's another actually because there's another SVM based theoretical exercise, and for that you definitely need to know the SVM dual SVM problem in detail, otherwise you cannot solve that exercise. So we will be covering that in the next tutorial, right? Because my plan is that I give you at least one tutorial off at the end so that there's no new material for you guys, and we can discuss it some basic questions again in the last tutorial, but we cover it at least by 3rd of February. We know everything what could be asked in the exam. So we have to, okay, so then you have to bear with me in this dual solve dual SVM problem solution. Okay, so yeah, so so if you look at when we will look in the lecture note in the next lecture in question 8:30, right? So we have to implement basically that equation into the solution. You don't need to know what is happening in that equation because if I am going to teach you that today, then it would take some time. It is a complete lecture. So let's just say that we are going to implement that, and we're using the solvers from the convex optimization library. Okay, and then again we define these matrices. which are defined in the equation 830, right? And yeah, I think maybe it is a good idea if I just show you at least the equation 830. Yeah, that would be okay. Let me just find my lecture notes. Okay. Yeah, that's equation 830. Can you see my screen, or is it paused?
We still watch see the lab solution,
Okay.
not the other windows.
Hmm. I think now
And
you
now
can
we
see.
see it.
Yeah.
Yeah.
So, so this is the equation 8.3 we are talking about. Okay, in the lab. So we have to implement this equation in the form of this convex optimization problem. So, for example, I think as already mentioned in the lecture notes, so we could also use MATLAB, and then we would use this quad prog function. So like this is just one implementation which we are discussing here in this tutorial, like so. And again, we did not went deep into how this convex optimization library is actually calculating this, and how to form this PG matrices, right? So with the help of these two examples, for example, if this is a data set, and this is like what you can say a toy data set. So we already know what is x1 and x2 and x3 x4 and all the labels. So we just want to see whether uh, it satisfies this KKT conditions, right? KKT condition, I think you guys have already covered for the theorem 8.2. Okay, so this is just this basic exercise. So again, we have this x troy, right? And we have 1 minus 2 1 2. So this 1 minus 1 is coming from x1, right? Then we have the first entry, okay, from minus 2, and it is coming here. Okay, maybe I zoom in a little bit. And then we have again from the first row of x3. So we have this in this form, and then we have an if we form make it an array. Similarly, second row, okay. I think this is quite straightforward. And then we have again the label data, okay. And then what we do is that we form the H toy. Okay, so H would be like this H matrix. Okay, and then if we form the H toy, right? And I think the equation was that would also be already mentioned in the lecture notes. Hmm. Okay. Yeah. So I think we will also discuss. I think now I'm feeling that you guys would really benefit if we also do it after also we will also go through the solution again after you have covered that from the lecture note, because the calculation of this H2I is also a bit involved, and I mean in this program in this programmatically it's quite simple. Like we are taking some some dot products and blah blah blah, and write carry some diagonal matrices. So it's quite straightforward here. But you should know what this H matrix is where this matrix is coming from, and what its actual role, in calculating um, the lambda star or the optimal solution. So today we will just quickly go through it, and we will go through it again in the next tutorial. Okay. So yeah, then we solve this. Then we use this solve dual problem function which we created here, right? And we just solve this dual problem, and then we have this lambda star solution, which is the optimal solution for this toy data set. Okay. And okay, and then we see that uh, only the KKT coefficient that belong to the support vectors are significantly larger than zero. So this is really important for us to know that the coefficients which are significantly larger than zero, because for example, if you look at here 6.5 into 10 to the minus 9, and again here 6.5 to 10 to the minus 9, these are like quite low. So these would be in some sense not very effective solution. So the coefficients which belongs to the support vectors would always be significantly larger than zero. So in this case, it would be this 2.5, right? I mean, this solution is quite simple, and we can actually visualize it because we are able to do that because we know the we know the whole data set, and we know the whole distribution of it, right? But in practice, definitely when we, for example, if we go to this X-train data set, and when we try to visualize that, then it would become quite difficult for us. Okay, but still, no, we tested this solved dual problem, right, on the storage data set, and then we want to test it again on the actual real data set, right? Then we write again the simple SVM, and then what we want to test is that how many test images were we able to correctly classify based on this training data, okay, and D1 and D2, and based on this dual solution of the SVM, right? And and as you can see that we have found an optimal solution, and the success rate is quite high. It's like 97. I mean, this is basically simple accuracy, right? So we have an accuracy of 97%. 97% of the time we are able to mm, distinguish between one and two digit, okay, which is pretty cool for such a simple machine or such a simple algorithm. So we can always try to make it more complicated, add some more tricks into it, and take this 97 to easily up to 99 or even more. Okay, so yeah, now we will take a short break because we have to again do this again anyhow for the after you have actually uh, gone through dual SVM in the lecture, and then we will go to the second part of the agenda, which is based on the variance and bias trade-off. Okay, so yeah, so let's join at 10 a.m. Germany time. So after 7 minutes. Okay, guys, so welcome back from the break. So, um, let's just talk about some curves, okay? I mean, it's a classic example, so it's really interesting one. Okay, so let's assume we have a simple model with only so let's just take that this is the price of the house. Okay, you want to buy a house, and this is the area of the house. Okay, and this is the data which you get from the market. And now you have three different machine learning based models which you train to get this data. I mean, from the training data, and you find because you want to predict for a certain area what would be. I mean, just assume that these are identical graphs. Okay, so so we have one model which is quite simple, and it's some sense a linear model. Okay, and then we have some model which is a polynomial model of high degree. Okay, and then we have some model. Okay, so which model do you think? I mean, what is happening here? Which model do you think is among these three is a good model? Please unmute yourself. Okay, let's just name them. This is one, and this is two. This is three. Hello. Hey. So anybody?
I think the first model is pretty good because it catches the overall trend, while the second one, like, it heavily overfits. So you might get some, like, the data points you have are pretty accurate, but the ones you would, like, if you put in some data points that are not in the model, that the model has
Who
not
is this
seen
speaking?
before. Sorry?
Who are you? I didn't get your name.
I'm Moritz.
What?
I'm Moritz.
Okay, so who is angry with Mr. M? Okay, please tell me. He's saying this is overfitted, Miss model number two. Maybe just
Yes,
using chat or say yes, yes,
yes, yes.
yes, yes. Okay, and what about model number three?
Yeah, I don't think it suits the data pretty well either, because, like, the overall trend is obviously going up with the area. So price is going up with the area. So I don't think that the third model catches that trend pretty well. Like, it's pretty good at the first few points, but for the right half of the points, it's pretty bad.
Yeah, so we can say that it's in some sense underfits, right?
Yeah.
So I actually just spin this graphs. So normally we have the linear model underfitting. People do that, okay? But I just want that you don't think in just fixed examples. You think, and it's you explained it pretty correctly uh, that the number two is overfitting and number three is in some sense underfits, and this is just right. So sometimes linear models are also just right. We don't need to say that they are like underfitting. Sometimes in practice, linear models are just right. Okay. So because I mean we are not interested in making more complicated models, so we are interested in making models which I mean for where the prediction error is low in some sense. Okay. So if the linear model is working fine, then that's good. So yeah, having said that, now let's go to what okay, maybe we also form some sense of bias and variance trade-off. Okay, so we have a model trained. Okay, so these are concentric circles. Just assume they are concentric. Okay, so this is real data. So and then we, the center or red point like this. Okay, let me just make it green. So this point is the ideal output which we want for a model to learn. But if your predictions are like scattered all over here, we would call this is a biased model. Okay, because it's biased towards a particular set of solutions. Okay, so this would be a biased solution because all the predictions, these are like each dot is a prediction is in a specific area in the solution space. Okay, okay, and let's just consider another model. Okay, so this yellow model, what would you call this model? Is it biased? Please tell me. Hello? No, yeah, that's right, Jin. It's not biased. I just want that you are also able to like visualize this thing, what's happening in the solution space. So this yellow is pretty unbiased because it's all over the solution space. So it's not biased toward a particular set of or there's no strong inclination towards a certain towards a certain portion of the solution space, right? So the predictions are all over the area, but it has very high variance because it is around the ideal point, but it's not exactly at the ideal point. Okay, and then let's say we have another solution. Which color should we give it? Let's give it black color. Okay, so this one, it has just right bias. Oh, okay, bias and just right variance. Okay,
One question: how do you define just right? Is it like super subjective?
it's super subjective. Exactly. Yeah. So when you are actually dealing a real problem, it is super subjective because you need a very intensive domain knowledge to calculate what is just right. I mean, we have some tools, we have some measures where we can say that we have enough bias or not. But at the end of the day, this just right is very subjective. And yeah, this is an excellent question. So this is what also I want to highlight. That's why I'm saying it in exclamation marks that this is just our idea. Okay, that we need some experts to add information into it. Okay, so yeah, now we want to draw another curve to maybe explain this point in more detail or give some what you can say concreteness to this idea. So I mean, normally we say that we have a capacity. A model has a certain capacity is the ability of the model to learn. Okay, learn the complicated solutions. Okay, and then we have okay, so I'm first going to draw it and then we will discuss it. So normally, in the normal sense, you actually want to not rely on the subjectiveness, but you also have some objective, what you can say, objective measures there. But at the end of the day, the decision to make what kind of objective measurement is just right for you is also again a subjective question in practice. But okay, we will try to formalize it and see what how we can look at the problem. So let's say this is the bias. Okay, so in general, when the capacity of the model increases, the bias decreases. This is a general trend for the data. Okay, and when the capacity of the model increases, the variance increases. Okay, and yeah, I mean, then we say that this zone, this is optimal capacity. I mean, this is a just right point. Do you understand my point now?
Yes, thank you.
Yeah. So I mean, the point is that this is because I really like this question, because this is what happens. I mean, again, do you want that your problem is a bit more biased? I mean, can you afford bias in your model? Then it's okay. Then probably you could shift this point up till here, right? So, okay, I can afford more bias. It's okay, right? But if you say, okay, no, we don't want any bias in the algorithm, then you can, okay, you can shift this point up till here, right? And you pay the price with the variance. So there's always a trade-off between bias and variance, and you have to live with that. There is no free lunch. Okay, you have to find out what fits your problem quite well. Okay, but I'm not talking just in theory, because this is the optimal capacity which we want, right? And normally we want it here. So there is another idea, which is this generalization error. Okay, in I'm going to make the generalization error in yellow. Okay, so let's say this generalization error. So this is your generalization error. You guys are already familiar with the generalization error, right? So can anybody tell me what is the generalization error? Please. If not, then I can explain.
I might have to guess, but I think it's the if we have trained a model and we use test data and then plot the error of classification. Is it something like this?
Yeah, it is something on these lines, but I think you guys, Rayan, did not discuss this generalization error, right? I will discuss it today. If not, please tell me at least through yes, no, or any means. Other guys?
Yes, I would like to maybe know the correct definition.
Okay. Yeah. So I just want to say that this is okay. Maybe I draw this curve a bit wrong because nothing like this happens. The generalization error is is never below this variance curve. Okay, something like this. So we want this generalization error, and we can also say, okay, wherever the generalization error is low, we want that point. So maybe I just try to make it a bit different than the. So maybe the lowest point is here. I want to make it here. Okay, so this is the lowest point. So again, no, you can just perfectly balance the bias or variance, or you can say, okay, I am only interested in the generalization error. Okay, so it's up to you. What do you want to choose? Okay, so normally the total error which we calculate in this generalization error, it could be like this. In some scenario, it is some function of bias plus variance plus Bayes error. Okay. So we discussed the Bayes error in the class earlier, or not? Guys, this has to be interactive, otherwise this won't work. Hello?
I'm not sure, to be honest, what Bayes error is.
Okay. I mean, Bayes error, or I mean, this is just one name. You could also call it some. I mean, the error which cannot be which can't be overcome. Okay. We have to just live with this. So, for example, in this case, if you create this this black cloud, right? This black cloud. So it is not exactly on this green point, right? And this is what happens all the time in the practice, because you're close to the target. I mean, you may have some points also in here around the target, but there's always some error which remains no matter what kind of model you use. And this you can call it Bayes error, or maybe irreducible error. So this represents the noise, and it is basically it is the noise which is in the data itself. Okay. And I mean, if you have hypothetically, if you have infinite data available, then you could probably also try to reduce this error to zero, right? If you have infinite resources and infinite data available, then it could be zero. But in practice, we don't have infinite data, so we have something with there's noise in the data, and we're not able to overcome that noise. Okay. So, for example, in the case of MNX digits, you have some noise in the data, and you can never reduce it to zero. I mean, because there's no like perfectly formed ones and twos, or like eights or seven and ones will always overlap with each other. Because sometimes when you write seven, it could look like one, right, to the machine. So it is basically coming from there. Okay. So let's just say it is because of the noise in the data. Okay, we are calling it loosely noise, and it is not removable. Okay. Yeah. I hope this answers your questions. Do you guys understand this point or not?
I think I get it. Thank you.
Okay. Okay. Now, coming from this perspective of this this high bias area, right? And what's happening there? So let's just maybe we see the error as our benchmark against which we measure the bias and the variance. So normally what would happen is that if you have a high bias problem, I mean, how to detect it, right? Let's just talk about that. That is my data or is my model suffering from the high bias problem, right? Then if you have, let's say, this training epochs, okay, and you have a model like this, okay, and this is the training error, right? And if you're also monitoring your validation error, or let's say your testing error at the same time, and you see that, well, so again, in some scenarios, this could be the ideal solution, right? Because you have your training error at the top of your test error, right? This is what you want. But it again, like the subjective question came into discussion earlier, it depends upon where this thing is. Is this acceptable to you? Let's say it is. What is exactly is epoch? Please, when I'm writing, it's quite difficult for me to look at the chat. So it would be good if you just open the mic and ask. Yes, epoch is the amount of training. Epoch is roughly defined as, for example, you have, let's say, 10,000 images for training. And when the model sees all those images, then we call it one epoch. And then we send the model again all those images, then this is second epoch, right? So it is the iteration of the training images again and again. Okay. One epoch is one episode where the model has seen all the training images. Yep. Yeah. So I was saying that now this thing is quite tricky, because if you want, if this is quite high, then you say, okay, well, this is a high bias problem. And if this is not quite high, this is like, I don't know, zero, this is less than 0.1, and this is acceptable to you, whatever error, right? And you said the error is 0.1, I'm happy, then it's good, then this is the ideal solution. But if this value, for example, if you have an image classification task and this value, this error rate is, let's say 0.3, and you say, no, this is not acceptable, that, okay, this is zero error, right? And this is error all the time. Okay, then you say that, well, oh, then you say that, well, this error is not acceptable to me. So this thing varies from problem to problem. So in cases where we have, according to our benchmark, if this is quite high, then we say this is, I mean, the training error is quite high, so this is a high bias problem. Normally, if you have a high bias problem, then this test error would also be a little bit higher than the training error. Okay, but it could even be lower than the training error. Sometimes this is some degenerate cases where this could happen, where your test set was very easy, then this could also happen. But still the error is quite high, so you do not want this. Okay, I hope this is clear. So now we want to make another curve, and we say, well, this is so again, on the error I'll achieve 0.01 right here, and for the, so this is the training time, again epochs here, and error. Okay, and this is, let's say, 0.2. Okay, so again, you would be quite happy that your model is training quite well and you have a very good, very low training error, but your test error is quite high. So then we would say that this model is having some high variance problem. Any questions here? Any questions here? No question?
One question maybe.
Yeah.
Like from this plot, it seems to me that maybe the data is overfitted also, because the test error is much higher than the training error, isn't it?
Yes. So you're absolutely right. So this high variance problem is normally also linked with overfitting problem. So if you remember this curve which we drew here, so this model is also suffering from overfitting, or from high variance. Okay. This is also high variance problem. If you dig into this, because then it is all over the solution space. We just want to, we're targeting this kind of behavior, right? This was our ideal behavior. We don't want model to be all over the place. It is perfectly fitting the training data, but when a new test data comes in, right? For example, if you're interested in knowing the price here, right? Okay, so ideally maybe the price would be here, right? But our model will predict this point. So do you understand that this would?
Yes.
Yeah. So again, for example, here, maybe the actual price would be here, but we have a very high variance problem. So you have to keep all these pictures in mind. So that's why I do this diagram, so that you know that we have a target, and if our solution space is all over the place, the prediction of the models, then it is an indication of the high variance problem. And again, this high variance is quite related to overfitting problem.
So can we say that overfitting easily leads to a high variance problem? Like in some kind
Yeah. I mean, normally what people say is this can be said definitely. They are quite related, but there are also some nuances which should be taken care of. For example, when you say the model is overfitting, then we say that this is because of the reason that model is learning the training data quite well, but is unable to perform at the test data. Okay, so then we say the model is overfitting. Okay, and this might be due to high variance. So high variance is one of the reasons, but there could also be other reasons for the overfitting. One reason could be that you did not uh, uh, change your training set in a very representative way. So the data you had was quite biased, or quite the data split is not justified. You know.
Okay. Yes.
Yeah, and there are also some other things. We will go into that sooner. So this could be an indication of high variance, right? I mean, practice, what we want is we want a model like this. I mean, this is what we want. If we have this training error, and then we have a very low test error, and both these values, this is like this epsilon, which is acceptable to us, right? And right, okay, let's call it delta. We have this delta value, which is acceptable error threshold, and this is delta plus epsilon, however we define it. Okay, so delta is the acceptable error, right? Right, and the epsilon is quite small number. Okay, normally it is we say that if it is a 0 point, I mean, this is just rule of thumb. This is not like because it varies a lot from the problem to problem. So if we are like between 0.1 to 0.1, then we are fine. Okay, so you could think of it if let's say, or maybe more concretely, I think it would be better if we write it like this: 1 plus epsilon into delta, right? So we see that if it is 1% to 10% of the training error, then it is okay. So we say it's a good solution. Okay. So this delta, this acceptable error, again is linked to. I mean, if we have this model, then this is just right. So do you understand how I'm trying to quantify it?
Yes, for me it's clear.
Thank you. Okay, so let's just use. There's a very interesting deep learning researcher. I mean, Dr. Andrew Ng, and I really like his style. So he actually had some things to talk about the high bias problem, right? And I'm just going to talk about that here, because I think this is very interesting for you guys, because these are things you should No, definitely, because you took this introduction to machine learning type course, this basic course. So you should know at least these things. These are really the basics. Okay, so if we have a high bias problem, sometimes it goes away if you train longer. Okay, if you train longer, this problem sometimes go away. So these are all just techniques. Sometimes even if you train longer, the problem will even be quite worse. You know. So, but still, this is one of the techniques. So, I mean, let me just pause here. Okay, we were talking about this good solution. Okay, but what if I accidentally or mistakenly I stopped at this point, my training? Then this would be quite. I mean, this error rate would be quite bigger than the delta, and this epsilon would also be not satisfied. Then I would say, oh, I have a high bias problem or high variance problem, right? But as I trained longer and longer, the problem would go away, right? So sometimes this also helps, just training longer. Okay, and like, I don't know, in 10% of the cases it might help, but in most of the cases this doesn't help. Okay, number two is increase the capacity of the model. The capacity is actually a very technical word, and I do not want to go into too much detail. So let's just say complexity of the model. Okay, if you're only looking into the uh, into the linear family, just look at the polynomial family, or look at the include some more uh, generalize or increase the solution space. Okay, where you're looking for the model training. Okay, so for example, if you're only looking for the linear models, then probably you will definitely in most cases experience the bias problem, right? So increase the capacity of the model. I hope this point is clear. I mean, these are the things which should be clear in your mind. Okay, so for example, if you have like feature based models, like the most models which we have studied are feature based features. So for example, we were just looking at the problem of this housing, right? Okay, I think it's okay if I draw it again. It would be still fine. So if we are looking at this housing problem, right? Okay, so we are only looking at the area, right? This is only one feature, one feature. So maybe this one feature alone is not able to explain the price. This is oversimplistic from our part. Don't you agree, guys? Don't you agree?
Yes, I agree. You could add something like the number of rooms or like an overall location.
Yeah.
thing.
You could add exactly number of rooms, right? The location is very important, right? You could also add year of construction, right? This could also be important. And yeah, location. I mean, location is, I mean, we know from experience that location is very important. So maybe all these, the prices, the data which we get here, maybe this was bigger, but the location was not good, this point. So the location was not good. That's why it was so low. But we don't see it if we have only one dimensional view of the reality, okay, of the data. So this is really important. So sometimes, and this is also just adding again to these were missing, right? And this missing thing also contributes to generalization error. this base error or this irreducible error, because you are not giving the model complete information. How is the model supposed to know all this? Because he knows only things which you tell him, right? So if you miss out important information, then the model is going to, I mean, there is always going to be some error, right? Because the model doesn't know I mean, why is this happening? So for example, I'm just going to say that uh, if we have let's say if I mean, you could have like here also a point here, right? Or maybe a point here, and maybe these points uh, are based upon the premise or the idea that these locations are like sent I mean closer to the city center, right? So the machine doesn't know all this information, so that's why we also, I mean, this is one of the sources of uh, of noise in the data and bias in the data. Okay, so where were we? Let's go back. So increase the number of feature also helps sometimes. And then number 4, uh, we can introduce or we can decrease the regularization. I think we have not covered the regularization in this lecture, right? So regularization is actually a quite broad concept, and probably it's good that if we study it separately, if time allows us in this lecture, because regularization is quite important concept in machine learning and deep learning, and just because of regularization, the model's performance could improve by up to 50%. You don't change anything, you don't change any training algorithm, you don't change any um, loss function or any training data, just using the regularization smartly. So so let's just skip this thing, probably out of scope for us now. But this could be one of the ways that you could get rid of this high bias problem. Okay. So so what is the idea? I mean, when in practice, when we are like, let's say we are at Marketiu at this is an e-commerce company, right? When we are actually creating a new model for a problem, right? We first create the data. There are like different steps. Let's say we have all the data, we have everything available, and then we say, okay, just start training the model, right? Training the model, whatever the model is. So this is like the first step. And interestingly, what we are focusing at is first, at the first step, we just want to mimic, or we just want to, like um, copy the behavior of the training data. I mean, if our model is not able to predict what ground truth he already knows, then what is going what good is this model would be for, for unseen data. I mean, if it cannot learn the seen data well enough, then then forget about the unseen data, right? So if, let's say, if you're talking about this scenario, if we have a load test error, this could also happen, but we are not going to uh, be content with this, because we I mean, at least we should have some confidence that this training error should be low, that we know that the model knows this and can predict this quite well. So this is what uh, what training error tells us. So at test time, right, it may happen that this goes down, but it may happen this goes up, because we have some practical data coming up, right, or some from the real world. So if this scenario for us, I mean, if we have this curve, test curve, or this test curve, it is equally bad for us, because we are not passing the first test, which is have a very low training error, right? achieve low training error? Low is again subjective, right? And again, how to lower it? Normally, this is because the bias problem and all the steps which we have mentioned here, they help in lowering that training error. Okay. Okay. So now let's go to the step number 3. Now we have achieved the low training error. We are happy, but we have high. Uh, now the second step would be, or sorry, the first step would be achieve low test error. Some people call it validation error also. I'm just going to comment it on it a little bit. Okay. And once you have achieved low test error, then your job is done. This is the basic idea. And how to get rid of how to achieve low test error or validation error. You have to get rid of the variance problem, right? That overfitting thing. Because in practice we can use high complexity model and the bias problem is solved easily, but this variance problem is more tricky. So let's just talk about the variance problem, how to lower it. So the tips we have is number 1, obtain more data. This is this cannot be emphasized enough. Obtain more data, because sometimes we are focusing, we have, let's say, even if 1000 images for training an image classification model, then this would not be enough because you are using a very high complexity model, and the filters are not able to learn a good representation of the data, just because the data is quite small. So that's why the deep learning has kicked off, because now we have more and more data and we can use very deeper neural networks to train them, right? And we get rid of this bias problem. Okay, so this is one way to reduce the variance by achieving by getting more and more training data. Okay, and increase the capacity of the model is the second step. Okay, and the third step is, it could be that we increase the regularization, which I talked about. I'm just writing it down for completion reasons, because regularization is a quite broad topic. Okay, and if you are, I'm just going to write in a different color. And if you are not using deep neural networks, you're using normal machine learning algorithms like SVMs or let's say support vector machines, or maybe yeah, let's just stick to SVMs. Then what you also want is that you have a very low you decrease the number of features, right? In that case, because there's too much information, and that's why probably you're suffering with a various problem. There are too many features. You have added too many features for learning the price or predicting the price of of your of your of the house, right? And probably the number of features are the source of the variance. Okay. Okay, just remember that this number 4 and 1 are different. These are different things. They are not linked.
I got a question.
Yes.
When we increase the capacity of the model, isn't when we have too high variance, our model memorizes too much information that is not necessary and creates a model that doesn't fit. Shouldn't we decrease the capacity of the model then?
Yes, we should decrease. This is what I wrote. Oh, no, I wrote increase. Sorry. You're right.
Ah, well, okay, that makes more sense.
No, sorry, decrease the complexity of the model. Yeah. So yeah, you're exactly on point. We should decrease the capacity of, sorry, I wrote it increase. So, I mean, because we are already in the variance domain, it is opposite to the, in the high bias, we increase the capacity, right? And in high variance, we decrease the capacity because our model is already memorizing too much information and we don't want that, right? Yeah. Thanks for highlighting it. Okay, so guys, any other questions or comments on this? I hope you guys did you guys understood something, and did you learn from today's discussion on this high variance things? I hope you learned something.
I like the graphs a lot, to be honest.
Okay. Yeah. So this is really interesting because these are the things you should every guy who's has any course in the machine learning should know. I mean, probably most of these things would not be in the paper. Uh, but I just wanted that you guys understand these things, because when you are going to do any project in practice, you should have this schema in work in your mind, right? Especially this idea. So this is the idea. You choose a model. I mean, there are also some steps before that, right? Definitely, there are always more steps. So I mean, like you choose the data, or create the data, right? Or you get the data. But that was not the focus of our talk today, so that's why I not highlighted it. So you get the data, right? You filter it, you clean it, right? Let's just say prepare data, so that we know prepare data set, right? And number 3, these are like pre-processing steps, and choose the model, right? You have to choose some model. And once you have done all those steps, then you start training the model. Then you try to achieve a low training error. And if the bias problem is not solved, right, then you're stuck there. You have to then maybe change the model, right? We already discussed that in the bias thing, that you have to increase the capacity of the model, right? Only one thing, this regularization is also one thing which you should know, but let's see if we have some time left. In the next tutorial, we will discuss something about regularization. So yeah, that's all for today. If you have any question, please ask me. Um, Otherwise, we can just finish it a bit earlier. Hello, guys. Ding ding. Any questions?
Maybe I have a final question.
Yes, yes.
So in the steps you described, decreasing the bias and decreasing the variance seem to be like going in opposite directions, right? So we have to iterate between those. Is that correct? So if I manage to decrease my variance, in the end, I have to check that my bias is still very low, right?
Yeah. So this is that's why it's called a trade-off. So because if you increase something,
Mm-hmm.
I mean, if you increase the capacity of the model, you get rid of the bias problem. But if you increased it too much, right?
Mm-hmm.
You're here, then probably the variance would be too much.
Yes, I was referring to the steps you presented to us in the end, at the end.
These steps.
So step 3 was like achieving the low test error, and step 4 was achieving the low validation error.
Yes, yes.
So 2 and 3, yes. So we're like iterating between 2 and 3 to get our trade-off, to find the point.
We are
right?
iterating over all these steps, man. I mean,
Okay,
these,
yeah. Oh, yeah,
yeah,
true. Okay, yes.
yeah,
Yeah,
because for
sorry.
example, if you look at the variance, I am saying obtain more data. So that is the step number one.
Mm-hmm.
Because in practice, in real life, things are like always connected with each other, you know. So from this step, you have to go to again this step.
Okay.
So all the steps are like are interchangeable, right?
Okay. Thank you.
Okay, just one comment on the on this point where I said some people call it validation error and some call it test error. I just want to add one thing, and I think we also have time, like we have 10 minutes. Okay, so what is a data set split? This is also important. Okay, so we have three kinds of data set. We normally divide data into three points. So one is training set. The second is validation set, and the third is test set. Okay, so they have all, I mean, these have their purposes. So when you have real data, then you have to create these kind of things. So normally before the dawn of machine learning, deep learning, people normally used 60 to 80% of the data for training and machine learning. Let me write ML before it. And let's say 10 to 12% for validation, and similarly 5 to 12% for test error. So this was like the rule of thumb. Okay, when we had this deep learning revolution coming about, because it needs a lot of data, the deep learning. So normally now it is between 90 to 98%, and this is 5 to 1 to 5%. And this is also 1 to 1 to 5, because the deep learning models are quite data hungry. That's why for training we need a lot of data. Okay, so this is the data percentage. Okay. Okay, so what is the purpose of this training set? Can somebody tell me the purpose of training set?
Yeah, that's the set we use to fit our model to like the data.
Yes, exactly. Absolutely right. This is the purpose. So I'm just going to write it in different words. Learn the parameters of the model, right? And the purpose of the validation set is learn what? Learn the hyperparameters. Okay. Hyperparameters are those parameters which are not learned during the training, but we just iterate over them. So for example, one hyperparameter could be the number of layers in a deep neural network, right? Or the number of neurons in one layer, right? So that would not be a parameter, that would be a hyperparameter. Okay. So the people who use this validation set, they have this very well-defined notion of what it could be used for, right? So because the training set, the idea is that you don't learn anything on the training set, right? So for example, when we were looking at these curves, so we were looking what was a test error, right? We were looking at something. But in practice, when you make a product, right? When you have, let's say, an app to classify the image of a cat and a dog, right? So you won't have the test data. Test data is when it would be deployed in the real world, and then you will see what is the performance. So you don't have it pre-hand. So that's why you create it or you call it the validation set, right? Because it is not the data which is being created runtime, but you are getting it already from your data sources from which you collected the data. Okay, So yeah, some people distinguish between them. I just wanted you guys to know that what is this training set and what is this validation set and what is this test set. So test set, you do not want to learn anything on it. You just no learning of any kind, right? Okay, is that clear?
Yes, it's clear to me. Thank you.
Okay, so yeah, just okay, just another okay, I'm just saving these so that maybe if you guys need it. Okay, just one more thing. Again, with this validation thing, they have many ideas. So some people call that we are using this cross validation concept. Validation, okay. Okay, some people call it k-fold cross validation. Okay. So what is the idea? So the idea is that you have this training set, okay, and you divide this training set into k folds. One, two, one, two. Okay. So what you do is that you use data set. This is your whole data set. You use k minus 1 folds or parts of the data, right? Of data for training or other training set. And then you validate or measure the performance on the kth fold. And then you repeat this process k times. Repeat it k times. Does this make sense to you guys? Hello? There's still 25 people.
For me,
Jinhu?
it makes sense. Yeah,
What?
but I'm not sure about the others. For me, it makes sense.
Okay, so Batu Khan, would you care to tell me, does it make sense to you or not? Or should I explain it more?
Can you hear me?
Yeah, I can hear you.
Mhm.
Yes, please, go ahead.
What will I say? I didn't understand.
You didn't understand. So I mean, the idea is that you have the data set, and if you have a fixed validation set, then it may be a problem that there is some drift in the data, you know.
Yeah.
Hmm.
Yeah.
So let's just remove this, because this is very difficult to remove, man. Okay, I just want, we have still some time so that you guys understand this thing also. This is, yeah. So the idea of the cross validation, I mean, one thing is that it shuffles the data, right? Shuffles the validation set. So for example, if you see this figure, right, this guy, it was easy, right? This guy was easy itself. So you could achieve even lower than the training one. I mean, intuitively, this should not happen, right? Why is this happening? If you are doing a k cross validation thing, then this you will not see this thing, because it can never be that you will, because you are averaging over all the k folds. You're treating each of them as a validation set or as a test set, right? So you would not see this behavior that your error is lower than the training set itself. You know what I mean? So that you have a very realistic estimate of your errors. So this is so it shuffles the training validation set, because there could be, I mean, like, the advantage is there could be easy samples in a fixed setting, in a fixed validation set, which leads to a very optimistic expectation or optimistic estimate of performance of the model. Okay, yeah. Is now it is it now clear to you?
Yes, clear.
Yeah.
But what if we have a very big data set? What we are going to do? We are going to still apply a these things.
Yeah. Again, now this thing is also very, because I'm very happy that you guys are asking these kind of questions. It means that you are thinking, how will we do it in practice? So this is exactly why this K cross fold validation was very popular when deep learning was not very popular. You know, so when machine learning was popular, when you had little data sets, then this K cross fold validation was quite popular, and it helped improve the performance of the models, or at least have a very good expectation of how it would work in practice. But with the dawn of deep learning, now you have like millions of images, or sometimes billions of images. So you do not want to train like 5 different, because the drawback is that you are repeating this process k times, right? So you're training k different models. So this is very, very expensive in practice, and you do not want to do that. So to answer your question, in the deep learning area, it may help, but you have to estimate that. I mean, you have to be quite satisfied with the validation split you made. So it's not easy split; it's a very representative split, right? So they're not. It's not what you can say, um, overcrowded with a particular style of samples. You know. So this is what we expect, and that's why we assume that uh, if you have large enough training set, then it would already be diversified. So this is also one of the reasons that if you see here, you have quite large training set, like 90 to 98%. So you are assuming that we have already uh, achieved what you can say. We have already seen all the examples which could be in the validation set of the same style, or which follow the same distribution, right? I hope this answers your question.
Yes, thank you very much.
Okay, guys, I hope today's lecture was helpful for you people.